Good morning, good afternoon, or good night, whatever it might be. This is your gear ratio worksheet notes. And feel free to stop this at any time so you can write down those four notes that you see down here as far as determining what gear a bicycle's in. First thing you're going to do is look at the number of gears that they have up by the pedals. So you look at your pedals and let's say there's 2 sprockets up there. Then you're going to look at how many sprockets or gears you got down by the back wheel. And let's just say there's 2 up by the pedals and there's 5 gears down by the wheels. That means there's 10 different possible combinations you could be that the chain could be in. You could be in the big gear up on the pedals and any of the 5 in the back, or the small gear by the pedals and any of the 5 in the back. To determine what number you're in, you need to determine, first of all, if the chain is on the large or small gear by the pedals. Now, the small gear up by the pedals is your lower number. So if you had a 10-speed bike, for instance, that means you'd be in gears 1 through 5. If the chain was on the big gear up by your pedals, that means you'd be in the higher numbers of 6 through 10. Well, after you determine that, look at the back gear, back by the wheel of your bike. And if the largest gear, if the chain's on the largest gear back there, that's actually your lowest number. The smallest gear, or those gear with the smallest radius, would be your highest number. So let's put all this together now. If the chain is on the smallest gear by the pedals, once again, the smallest gear by the pedals, that's going to be the lower number gears, like 1 through 5. And the smallest gear on the back wheel, you got to remember, that's flip-flop. The smallest gear on the back wheel is your highest number. So that means your gear would be in 5th gear, because it would be the highest number of gears 1 through 5. Now let me expand on that. If the chain was on the largest gear up by the pedals, well, that means you're in gears 6 through 10. But it's also on the largest gear on the back wheel. Now remember, the largest wheel on the back wheel, that means it's the lowest number because it flip-flops. That means you would be in gear 6. So feel free to, once again, stop all this, write this down. Now we're going to do some sample problems on the next page. So if you follow this worksheet down, you'll see the sample problems. And I need to take you back to when we did simple machines and the formulas for mechanical advantage, ideal mechanical advantage, and efficiency. And that's all up here. And I've got to remember, for mechanical advantage, it was force out over force in. And you have to remember that you're going to put the force in on the pedal and it's going to come out on the chain. And then in the rear wheel, the force is going to go in on the chain, but the force comes out on the back wheel. So we're going to constantly multiply all these things together to get the mechanical advantage. So let's do some problems here and I'll show you what I mean by that. I'm going to go to the next page. Now it says, what is the ideal mechanical advantage of the wheel and gear? So let's write this down if we possibly can. Hold on. Okay, so we got to remember that ideal mechanical advantage, or IMA, was the same thing as din, or distance in, over distance out. Well, if you're just looking at this wheel, you got to remember that the distance in is what you put in on the chain, on the gear rather. So we have a gear that has a 4 centimeter distance or radius, and the distance out comes out on the wheel. So once again, the chain puts it in on the gear, the distance comes out on the wheel. The wheel is 35.6 centimeters. And so your ideal mechanical advantage, now this is going to be extremely strange to you here, ends up being 0.112. Now, you got to remember that when we're talking about mechanical advantage, if I said mechanical advantage was 2, that means it's twice as easy. If the mechanical advantage is 3, that means it's 3 times as easy. Well, if you notice, this right here is less than 1. So the bike actually makes it harder to do the work. But what you're going to find out here is you get much more distance out. So you're sacrificing how hard it is to pump, because you get to use your body weight to push down with your legs, but you're sacrificing how hard it is to pump, and you're getting a lot more distance out. The next thing I ask is, what's the mechanical advantage of this wheel and gear system? Well, we have to go back here a little bit, because on mechanical advantage, we got to go back to the efficiency formula. With efficiency, you got to remember that efficiency was actual mechanical advantage over ideal mechanical advantage. And it's wanting you to find the actual mechanical advantage, which I'm putting a green star next to. Well, it says that the efficiency right down here is 95%. So I'm going to put 0.95 in for the efficiency, because 0.95 is the same thing as 95%. I'm then going to say AMA over my ideal mechanical advantage. Well, you got to remember, my ideal mechanical advantage is right up here at 0.112. So when you cross multiply, your actual mechanical advantage ends up being even lower. It ends up being 0.1064. So you don't even, it makes it even harder now because of friction on the road and all that sort of stuff. Part C says, what's the resistance force? Well, the way you get that, I'm running out of room here. Let me scroll this down a little bit if I can. The resistance force is in the actual mechanical advantage formula. If you remember, it was force out over force in. Well, your force out is what we call your resistance force, okay? And your force in was called your effort force, okay? So let's go ahead and figure out what this is. The actual mechanical advantage, once again, was 0.1064. The resistance force, or the force out, is what I'm trying to find, so I'm going to put an F out there. And the force that you put in, well, they said that you put in right up here 155 newtons. Everybody see that 155 up there that I just circled? Okay. And so what I'm going to do here is I'm going to cross multiply again. So your force out ends up equaling a total of 16.49 newtons, I hope, if I did that right. So 16.49 newtons. Lastly, but not leastly, it asks for how far it was the chain pulled to move the rim that amount. Well, let me see if I can stop this for a second because my smartboard is locked up like normal. Hang on. Okay, let's see if we do part D now. I think I'm back online. It says, how far was the chain pulled to move the rim that amount? Well, I'm going to go back up and use this ideal mechanical advantage formula and pull it down here. So I'm going to put ideal mechanical advantage equals din over doubt. Remember, I'm going to dine doubt. Once again, my ideal mechanical advantage was 0.112. And it wants to know how much distance we're going to have to put in on the chain if we get out 14 centimeters. So I'm looking for the distance in. Once again, they said you get out 14 centimeters on the wheel. Well, once again, we're going to cross multiply this. So this whole thing is cross multiplication. The distance in, 14 times 0.112 is 1.568 centimeters. Now, I want you to look at this. This is why we go ahead and ride bikes and we don't worry about if things get harder. Yes, the mechanical advantage up here said that things got a lot harder because its mechanical advantage was less than 1. But I want you to look at this. If you look at your thumb, the width of your thumb is about 1.5 centimeters. But for every 1.5 centimeters that you put in, you get out 14 centimeters. And 14 centimeters would be about the length of both hands put together. So you're getting out 10 times the distance that you put in. And so you don't worry about how hard things it is if you can go a lot farther distance. So hopefully that explains how a bike works. And we'll look at it in lab tomorrow and look at all the gears so you can see what's up. Thanks for getting all those notes. We'll talk at you tomorrow. Love you. Bye.